Okay, seventh grade. We're going to continue on with probability today with lesson 4. Today we're going to be learning about theoretical probability and how that differs from experimental probability. What we've been doing so far is experimental probability because we've been doing trials of things like shooting baskets over and over and over and counting the number of baskets you make. That's an example of a chance experiment, and if you record the results, you can estimate probability using the results of your data. So today we're going to do something with these Unifix cubes. I've got this bag filled with a bunch of yellow, blue, green, and red cubes, and I've actually already done the experiment. But the experiment is, okay, I pull out a cube, it's red, you mark it down. I pull out another cube, it's green, you mark it down. I pull out another cube, oh, I got a green again, you mark it down. So for each one of those, reach in and pull out a cube is what we call a trial, okay, in the experiment. And we do this 20 times. Let me zoom in now. And I've already done it because that's super boring for you to watch. And I recorded the results, okay, just like I did the other day with my husband in the cup. But that's what this is. This is the data from our chance experiment of pulling out a colored cube from a bag. And then I tallied up the results, and you can see that I got yellow 5 times, red 4 times, green 6 times, and blue 5 times. All those add up. These are the frequencies of each event. You know, the event would be, oh, I got a yellow. That's the yellow event, okay? The frequency was 5. So all those should add up to 20 because I did this 20 times. Okay, so now we're going to go through and answer questions about our experiment. And we're going to calculate what we're going to find to be the experimental probability. And then later on, when I reveal to you the exact number of cubes, we'll find out the theoretical probability. So number 1 says, based on the 20 trials, estimate the probability of choosing a yellow cube. So I want you to look how I wrote it. This is the notation we use with probability. P stands for probability, and the event, the name of the event that you're calculating the probability of, goes in the parentheses. So the probability of getting a yellow cube is going to be calculated, and this is the same formula from the slide that you should have already written down. The number of observed occurrences of the event. So the number of times we got a yellow cube, that would be an observed occurrence of the event, over the total cubes. Okay, well, we got 5 yellow out of 20 tries. That reduces to 1/4, or the decimal 2500ths, 0.25. For the green, the probability of green, the numerator is 6 because we got the green 6 times. Go back to the data. Here it is. You see by green I have 6. That means that's the number of times I observed a green cube. That's the numerator. And you reduce that, you put that over 20 because I did it 20 times. Reduce and get the decimal, and it's 0.3. Red, I only got 4 red. That was my lowest one. So that reduces to 1 out of 5, or 0.2. And blue was the same as yellow. It came exactly out to 0.25. So all of these probabilities that we just calculated are the estimated, or excuse me, experimental probabilities based on the experience that we got from this trial, or from this experiment, I should say. Okay? So we call these experimental probabilities, and we use them to estimate, if this is all we have, we use these to estimate, okay, what do you think the probability will be that I pull out a blue cube? Well, you look at your experimental probability and you say, oh, I bet you have a 1 in 4 chance of pulling out a blue based on what has happened in the past. Okay, so we can use this to predict how many of each color are in the bag. If there are 40 cubes in the bag, how many cubes of each color are in the bag? Well, let's use our experimental probabilities to predict, okay? If there are 40 cubes, we predict that 25% of them are going to be yellow because 25% of the time I pulled out a yellow cube. So 40 times 0.25 is 10. So you take your probability and you multiply it by the total, and that will give you your predicted number for each number of those cubes. So we predict there are 10 yellow, 12 green, 8 red, and 10 blue. And sure enough, all that adds up to 40 cubes. So that's how we're using experimental probability here to predict what we think is actually in the bag. Now, if I were to do this experiment again, this is number 3. If I were to do it again, now that you guys are all watching the video and I were to do it again right in front of you, do we expect that I would get the exact same results? Okay. What do you think? I'm going to pull cubes out at random 20 times. Do you think I'm going to get exactly 5, exactly 4 red, exactly 6 green, and so on? Hopefully you have the sense that no, I will not, because this is a chance experiment, okay? It's completely up to chance. There's no way to predict exactly how the numbers will fall. So they will be similar, but they will not be, we do not expect them to be exact, okay? Now, here's the big question. How many of each color are actually in the bag? Are our predictions accurate? Well, the truth of the matter is that there were actually 10 cubes of each color in the bag. So I had 10 blue, 10 yellow, 10 green, and 10 red. And that added up to 40. So now we can find the theoretical probability, which is, now that we know exactly how many yellow cubes there really are in the bag, then I can calculate the theoretical probability. And theoretical probability is calculated the same way, except for it's just a little bit different terminology. The number of favorable outcomes, in other words, how many yellow cubes are there in the bag? There are 10. So you put that over the number of possible outcomes. How many cubes are in the bag? 40. So in other words, I have 10 chances to pick a yellow cube out of 40 cubes altogether. And that's how you calculate the theoretical probability. It's based on what you actually know. And look at that, it's exactly the same as the experimental. So yellow and blue, our experimental probability came out to be exactly the same as the theoretical, which is kind of cool. But yeah, look at the green and the red. The green and the red also are 0.25 because there are the same number of cubes of each color. So these are all, each color is equally likely to be drawn because the probabilities are equal. So let's skip down to this question 5. That's what I was just getting ready to say. Is each color equally likely to be chosen? Explain your answer. Well, yes. We've already calculated the theoretical probabilities, which are all exactly equal. And we know for a fact that there are the same number of cubes for each color. So each color is equally likely to be chosen. Okay. Number 6 wants us to compare the theoretical probabilities of choosing each color to the experimental probabilities that you found in exercise 1. Okay. So compare the two. We already have a sense that they're very similar, but let's just write it down in a chart form so we can see them side by side. For yellow, if you remember, we calculated the experimental probability as 0.25, and then we found the theoretical probability to also be 0.25, so they were exactly the same. That's pretty amazing. That doesn't always happen that way. For the green, though, this is probably more realistic, that we got the experimental probability to be 0.3 or 0.3, but the theoretical was 0.25. So it was a little bit off. It was our experimental probability was about 0.05 too high, 500s too high. That's not very far off though, but it was a little off. And then same for the red, but just in the other direction. It was 0.05 too low, our experimental, than the theoretical. And then the blue was the same. So they're calculated similarly. Experimental is based on the number of successes you actually get when you do an experiment. The best way to think about experimental probability is something like shooting baskets, because you cannot know the theoretical probability of shooting baskets. There's just no way. Are you going to make it or not? We don't know. But we can do an experiment where we count, we sit there in front of the basketball goal and we shoot a bunch of baskets, and we count the number of attempts and the number of baskets, and we can use that to calculate an experimental probability. Theoretical probability can only be calculated if you know for a fact the number of successful outcomes you can get. Like, for example, having cubes in a bag. I know that there are 40 cubes in that bag and 10 of them are yellow, so I can calculate theoretical as 10 out of 40. All right, now let's go on to some more examples of chance experiments where we have to determine the sample space and then calculate the theoretical probability. So always in probability, you're going to have problems about flipping coins. That's very common. And it's helpful if you're ever asked questions about coin flipping that you be very clear about the first coin and the second coin. So the best way to do that is just to give them different names. Don't call them coins. Tell yourself, let's pretend that one's a nickel and one's a dime. And that's what they did in this first example. They didn't say just two coins. They said, think of the nickel as separate from the other coin. And the best way to do that is to think of them as different coins altogether. So what happens when you flip a nickel and a dime? What happens when you flip a nickel and a dime? What are the different things that could happen? What are the different outcomes? So the experiment is flipping a nickel and a dime. That's the experiment. The outcome is what could happen. And our job right now is to list all the ways that the two coins, the nickel and the dime, could land. They've asked us to complete the sample space below. Remember, the sample space is when you list all the different ways that all the different outcomes that an event could have. So the best way to do it is just to go through very methodically. The nickel could land on heads. Let's just pretend we're flipping the nickel first. It could land on heads. Now, leave that there and ask yourself, which way could the dime land? It could also land on heads, right? So if the nickel lands on heads, the dime could also land on heads. Now, is there any other way that could have happened? If the nickel landed on heads, stay with the nickel landing on heads for now. Just work your way through the only things that could happen if the nickel landed on heads. Well, the other thing that could happen is that if the nickel lands on heads is that the dime lands on tails. So this is kind of the language. If the nickel lands on heads, the dime could land on heads. However, if the nickel lands on heads, the dime could land on tails. Is there any other way for this to happen if the nickel lands on heads? No, we're done with the nickel landing on heads. There's no other possibilities. Now we switch to the nickel landing on tails, and we say, if the nickel lands on tails, what could happen to the dime? Well, it could land on either heads or tails. So hopefully you can see there are only 4 ways for these two coins to land. So this is our sample space right here. It is the list of all possible outcomes for these two coins to land. Now we're asked, what is the probability of flipping 2 heads? So this is theoretical probability because we're just looking at the sample space. We know for a fact all the possible outcomes that could happen in this event. So we don't need to do an experiment. We could sit here and flip coins and count them all up and get experimental probability. But since we know the sample space, we can just look at it and say, oh, look, out of all the possible outcomes, only one of them is 2 heads. So we say the probability of 2 heads, look at my notation here, is going to be 1 out of 4. So there's one favorable outcome. The favorable outcome is what you're looking for out of the total number of ways that this experiment could go. Okay, so that's the formula for theoretical probability. It is right here. You wrote it down from the slides, but it's the number of favorable outcomes. There was only one favorable outcome in our sample space out of the total possible outcomes, which was 4. Okay? All right, let's do the exercises 1 through 4. Consider a chance experiment of rolling a 6-sided number cube with the numbers 1 through 6 on the faces. So you guys are all familiar with those. I don't have one in front of me, but you guys know what they look like. And all cubes have 6 faces. And this is the sample space right here. 1, 2, 3, 4, 5, and 6. That's all the different ways that the number cube can land. And so if there are 6 different things that could happen, the probability of it landing on a 1 is only 1 out of 6. So that's my probability, 1/6. The probability of it landing on a 2 is still only 1 out of 6. There's only one way to get a 2, okay? And that's if the number cube lands on a 2. There's only one way to get a 3, only one way to get a 4, and so on. So the probability of each of those is 1/6. But what's the probability of rolling an odd number? Okay, so look at these and see which one of those is odd. Now, I included 1. Some people don't include 1. They say, oh, 1 is neither odd nor even. But I just went ahead and included it. I think of 1 as an odd number. It doesn't really matter. That's for another topic. So 1, 3, and 5 are the odd numbers. I would say there are 3 odd numbers in our sample space out of 6 total possibilities. So I have a 1/2 chance or a 0.5 chance of getting an odd number. What's the probability of rolling a number less than 5? Well, there are 4 numbers in our sample space less than 5. So the sample space is still the same. I think I'm a little bit confusing you by writing it this way. So I'm going to quickly fix that because I don't like it looking like it's the sample space. This isn't the sample space. Our sample space hasn't changed, okay? There are 3 possibilities, 1, 3, and 5. These are the number of favorable events, okay? That's what that is. That's the number of favorable. And here, the number of favorable events are 4. Okay, number of fav would be 1, 2, 3, and 4. Those are the outcomes that could happen from our sample space that are less than 5. So there were 4 favorable outcomes, 1, 2, 3, 4. So it's 4 out of 6. See, I still have the same sample space. Okay, the sample space doesn't change. Notice my denominator does not change. What changes is the numerator, which is the number of favorable outcomes, because the event that we're calculating the probability for changes. Okay, so I just wanted to be clear that I wasn't confusing you. So the probability of a number less than 5 is 4/6, which is 0.67. Okay, number 2, consider an experiment of randomly selecting a letter from the word number. So you have to imagine that the letters in this word are all maybe in a bag or an envelope, and we're just going to randomly pick a letter. What is our sample space? Here it is, NUMBER. That's our sample space. Okay. How many outcomes are in our sample space? 6. Okay. So each one of there are no repeats of those letters. So each one of those letters has 1 out of 6 chance of being picked. Okay. Now, this is what is the probability of selecting a vowel. Well, U and E are the only favorable outcomes. They're called favorable outcomes because that's what we're looking at now. The vowels are the favorable outcomes. Well, how many favorable outcomes are there? There are 2. So we would say the probability of getting a vowel would be 2 out of 6. Okay, so we listen to the language. I know I'm repeating myself a lot, but I'm doing it on purpose. There are 2 favorable outcomes if we're looking for the probability of selecting a vowel out of 6 possible outcomes. 2 are favorable out of the 6 total. That reduces to 1/3 or 0.3 repeating. What's the probability of selecting the letter Z? Ha! 0. It's impossible. There's no letter Z in the word number. So don't forget, it is possible to be asked for the probability of an event, which is impossible. And your answer will be 0. All right. Now, I think this is where, okay. Yeah, I think I messed up on one of these. So, yeah, okay. I'll get to that. So color the squares below so that the probability of selecting a blue square is 1/2. Okay, well, there are 10 squares. If the probability is going to be 1/2, that means the probability of selecting a blue or yellow have to be equally likely. So that means there have to be the same number of blue as yellow. Since there are 10 squares, I colored 5 blue. The other way you could look at it is if the probability is 1/2, okay, then I know I have to get the number of favorable out of the total possible, and I know there are 10 squares, so I know 10 has to be my denominator, and you just use your skills on equivalent fractions, because that's all this is an equivalent fraction, and you know that you need to color 5 blue, okay? Yeah, this is the one right here where I actually colored them wrong. Okay, because your paper will say color the squares below so that the probability of selecting a blue square is 4/5. Well, obviously I did this wrong. I did it backwards. So that's why I just quickly changed it to yellow because I colored it so that the probability of selecting a yellow was 4/5. So how I did that was I knew that I wanted my probability of my yellow to be 4/5. So I looked at the total number of outcomes. There are, or you know, the total. I could pick 10 different squares. Basically, is what I'm saying. Okay, so the number of favorable would need to be the number of yellow. Okay, and so if I have 4/5, I can convert the denominator just like I did before to 10. Because I have more than 5 here, I have 10. So using equivalent fractions, 4 times 2 is 8, and I knew I had to color 8 yellow, okay? So there are 8 yellow, that's the number of favorable out of the total possible, okay? All right, last one is 2 spinners, okay? This can be complicated. What they're asking you to do is to look at these 2 spinners, pretend that you're going to play a game where you need to spin both spinners, and you will quote unquote win if they both land on red. Okay? And the question is, what is the probability of that happening? So in order to calculate the theoretical probability, you have to write down the sample space. You have to know how many different ways are there for these 2 spinners to land. Not just one spinner, but the 2 of them together. Okay, so obviously this spinner can either land on red or blue. All right, so we're going to start with a more simple spinner, and we're going to only focus on what happens when that first spinner lands on red. because like I said, you want to be very methodical about it. Okay. Otherwise you get confused. So let me get like a little, I'm just looking for a little sticky note. There we go. So we're going to just start with the first spinner. If the first spinner lands on red, what could happen on the second spinner? And this is where you need to be methodical. It could land on red. There's my red for the second spinner. Still on red for the first spinner. It could land on blue. Still on red for my first spinner. It could land on yellow. Second spinner could land on yellow. Still on red for my first spinner. It could land on green. Now, are there any more ways for the second spinner to land? No. Now we know it's safe to move on to the first spinner landing on blue, and then you go through the same process. It will be blue, red, blue, 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 yellow, blue, green. And you just make sure you don't miss any. There should be 8, and there are 1, 2, 3, 4, 5, 6, 7, 8. So the sample space, well, I'll just leave the sample space written like that as a chart, okay? But how many of these outcomes consist of both spinners landing on red? Only the first one. So that's how I got my theoretical probability as 1 out of 8. All right? So good luck on the problem set. Please come to office hours if you have questions. Bye.